This video lecture discusses the transfer function of the first order linear dynamic system. Equation 1 is a first order linear differential equation. It represents the first order linear dynamic system. R of t is the input to the system, and this signal is in time domain. Y of t is the output of the system, and it is also in the time domain. The derivative of the output is of first order, therefore it is first order linear differential equation. A and B are the parameters. They are constant. This means they do not change with time. This is why we say equation 1 represents linear time invariant first order dynamic systems. If the initial conditions are 0, we can write the transfer function of the system. The Laplace transform of differential equation given in 1 can be written as S y of s minus y0 is the initial condition plus a y of s is equal to b r of s. In this equation, r of s is the input to the system in Laplace domain. S is a complex variable and it represents the frequency. Similarly, y of s is the output signal in Laplace variable domain and s is a complex variable. Y of 0 is the initial condition and we know it is equal to 0. Therefore, S y of s plus a y of s is equal to b r of s. This implies s plus a into y of s is equal to b r of s. Therefore, t of s is equal to y of s upon r of s is equal to b upon s plus a. Here this expression is known as the transfer function of the system. The transfer function of the system does not depend upon the input and output signal, but it depends upon the structure of the system and the elements of the system. Laplace transform of the output divided by Laplace transform of the input give us the transfer function, but the transfer function itself depends upon the system parameters and not on the input signal and output signals. This transfer function represents the first order dynamic system. Let us explain the transfer function of the system using this RC circuit. In this circuit, the resistor R and the capacitor C are connected with a input signal VI T. R and C are in series. The switch T is open for a very long time. This means the capacitor C is completely discharged. Capacitor C can store the energy, so it is a memory element, while the R does not store energy, therefore it is a non-memory element. Because in this circuit we have only one memory element, therefore it can be represented by the first order linear differential equation, because the capacitor and the resistor are considered linear. We consider voltage across the capacitor is VCT. This is the output voltage of the system, and this voltage is a response of the input voltage VIT. When we close the switch T, a current I will flow through the circuit, and this current is equal to C dVCT upon dt. Therefore, the voltage across the resistor is R C dVCT upon dt. According to the Kirchoff's voltage law, the sum of the voltage across the resistor and capacitor in this circuit is equal to the input signal. So R C dVCT, the voltage across the resistor, plus voltage across the capacitor is equal to the input voltage signal. In this equation, all the signals are in time domain. The initial condition Vc0 is equal to 0. This means when we close the switch, the capacitor was completely discharged. Therefore, the voltage across the capacitor at the closing time of the switch was 0. Now, taking the Laplace transform of the first order linear differential equation given in 1 can be written like this: R C into S VCS minus VC0 plus VCS is equal to VIS. Equation number 2 represents the same system, but now all the signals are in the Laplace variable. Here Vs is known as the Laplace variable in the honor of the mathematician Laplace. S is a complex variable and it represents the frequency of a signal. So the original equation 1, which is a first order linear differential equation, has been converted to the algebraic equation in the form of 2, but it represents the same system. Now the initial condition is 0, therefore we may write RCS VCS plus VCS is equal to VIS. This implies T of S, the transfer function of the system, is equal to VCS upon VIS is equal to 1 divided by RC S plus 1. In the standard format, we can write 1 divided by RC divided by S plus 1 over RC. This is the transfer function of the system shown in this figure. Here it is easy to note that the system transfer function depends upon the element and values of the elements and their topology of the connection. The transfer function does not depend upon the input and output signals. Let us consider another example. On this slide, we will explain the transfer function of the mechanical system. Here mass M is connected to the damper and the damper coefficient is F of V and the mass of the body is M. Then using the Newton law of motion, we can easily write M dVt upon dt is the force across the mass M, dVt upon dt is the acceleration of the mass M, plus Fv, the coefficient of the friction of the damper, multiplied by the velocity V of t is equal to the force F of t. Force is a function of the time and velocity is also function of the time. We consider initially the system was at rest. This means the initial velocity is equal to 0. Now taking the Laplace transform of equation number 1, we will obtain M S V S plus minus M V of 0 plus Fv into Vs is equal to F of S. The input signal force is now in the Laplace domain and the output signal V of S is now in the Laplace domain. S is a complex variable. Then we can rewrite equation number 2 in the following format as V of 0 is equal to 0. Therefore, M S plus F of V multiplied by V of S is equal to F of S. This implies T of S is equal to V of S upon F of S is equal to 1 over Ms plus Fv. It is easy to write this system as Ts is equal to Vs upon F of S is equal to 1 over M upon S plus Fv upon M. This is the transfer function of the system, which does not depend upon the output signal velocity and the input signal mass, but it depends upon the component attached to the mass, the damper and the mass itself. So the transfer function always represent the characteristics of the system and not the characteristics of the input and output signals. Thank you very much for listening this lecture.